Hello everyone and welcome back. Today the topic is Fluctuation Dissipation Theorem. This video will be a complement to my article in my website. So what is Fluctuation Dissipation Theorem? Well, it is a relationship between a fluctuation body and the dissipation on it. So think of a particle, a system that has many particles. So what we are proposing is that the amount of the movement in those particles, fluctuation, is related to the dissipation on a body that is near that particle. Well, it makes sense when you think about it. Because if a body tries to move in that media, and if that media has many particles in it, then that body will be bombarded by those particles, creating a dissipation on that body. So fluctuating particles have a correlation to the dissipation. Well, this relationship has been first discovered by Albert Einstein himself in 1905, his miraculous year, where he also developed the theory of relativity. So, Einstein used this relationship to discover the existence of molecules. He was able to correlate those fluctuations of the dust particles in Brownian motion to the dissipation, and via using Boltzmann's equation, and since we also know the Boltzmann constant, he was able to derive and calculate and predict the dimensions of those molecules. But the reason we are interested in this question of fluctuation dissipation theorem is the application of it to quantum mechanics. You see, the same relationship is so fundamental that it can be applicable to quantum mechanics, and mainly to quantum space. So in a way, this relationship can explain some fundamental properties of the quantum vacuum. So the noise of the quantum vacuum fluctuations are related to the dissipation of it in a way. But when someone thinks about an empty quantum space, how can a heat arise from that space? Many people would like to believe that, would like to imagine a quantum vacuum as the creation of particle and antiparticle pairs constantly, creating a fluctuation on the space. But these kind of approaches are quite, let's say, misconceived, because you see, it can only be applied for fermions. For bosons like photon, you cannot view space as like an antiparticle, since a photon's antiparticle is itself. So there are many ways where one can derive fluctuation dissipation theorem fundamentally from quantum mechanics. And the best, let's say, arena to do this is quantum optics, because of the lasers and other applications in laboratory, quantum optics has become, over like the last 3 or 4 decades, a very good field to introduce some of the fundamental principles of statistical mechanics to quantum mechanics. So this is the field where both disciplines have been merged most fundamentally. So one can see many applications and realizations of fluctuation dissipation theorem in quantum mechanics. But if you want to learn about this stuff, you can visit my website. I explain them all. So this is what you should do if you are interested in physics of it. But let's discuss, what does this mean? What does this mean is that, yes, you are talking about fluctuating particles and the dissipation that it creates. But in quantum mechanics, we are working on complex inner product space that is Cauchy convergent, which is Hilbert space by definition. These kind of mathematical structures that are behind quantum mechanics are very fundamental, and they work. But the issue is that, can we define an object, a realization that is so let's say, physical, like fluctuation dissipation theorem in this field. So how can we realize and build an intuition for this theorem in quantum mechanics? In a way, because what we are saying is that there's like a swarm of real particles that are fluctuating and creating heat. Well, they don't exist, those fluctuations, but they exist only in your measurement, so they don't exist arbitrarily by their own. Well, you would say that this guy is crazy, what is he talking about? But you see, this kind of like viewing objects in quantum mechanics is so, let's say, omnipresent. So every concept in quantum mechanics is realized like this. So it's not like, so quantum mechanical objects are not separate, cannot be separable from their effects. So quantum mechanical objects' existence, so the ontology of a quantum mechanical being, is only valid if it is correlated to an outcome. In a way, a quantum object doesn't exist by its own. It only exists because it creates results. So if something is observable at least, or if something's presence is observable, then we assume that object is existence. Well, philosophically and ontologically, this kind of approach, I think, cannot be appreciated, and this is the reason why many generations of physicists, including Einstein, disregarded quantum mechanics, because you are telling that no, the properties of that intrinsic object is not important, only the effects of it are important, and you can build a linear algebraic properties from those objects. So that object becomes a black box for you. You only know the input and the output, and that black box somehow creates that outputs. And that quantum vacuum is not separate from this explanation. As I explain you, somehow fluctuation dissipation theorem, somehow that mechanism at least works. We don't know how far that mechanism actually ticks behind the curtains of quantum mechanics, but it creates results. Well, is this something that we can accept as physicists? Well, in the end, what we scientists want is an outcome, is prediction. So we are getting our predictions. But as physicists who want to explain the mechanism, and for many physicists, the satisfaction of doing physics is to understand those mechanisms. So if you don't understand those mechanisms quite well, and if you don't know how, for example, the collapse of wave function actually works, we don't know about that as well, like fluctuation dissipation theorem. Why does it work? We don't know how, and the dynamics of like the collapse of wave function. So many physicists, including like Hooft and again Einstein, has developed their own interpretations of quantum mechanics, where they propose hidden variables, and I believe Hooft's version of quantum mechanics is called automata theory of quantum mechanics. It is similar to Einstein's, at least philosophically, it's similar to Einstein's, where he imposes hidden variables to the quantum system. So, when you think about it again, a quantum object by itself is a complex function. What is a complex function? You cannot visualize it. And this is actually similar to in electrical engineering. You have an AC source that can be decomposed into a complex sinusoid, but that doesn't correspond to anything. So, for example, in engineering, what we do, we disregard those kind of applications, and we assume that they are just mathematical tricks, but they still give the correct result. But in a way, in engineering and many other applications where the complex numbers are used, these kind of entities can be disregarded. They can be disregarded, let's say, that make you philosophically happy about the conjecture that I was talking about. But in quantum mechanics, every entity, every object in quantum sense is complex. So you cannot bypass this kind of philosophical argument. So I believe that we still have a long way to go, and we don't understand how quantum mechanics works. And quantum vacuum is something fundamental because it's the essence of space and time itself. So it's important for us to understand the mechanism behind it and why the quantum fluctuation and dissipation theorem work in this kind of arena. Since like when one also thinks about like since quantum mechanics is intrinsically probabilistic, then it should always like fluctuate in a sense. Then there is also a dissipation, and how should we physically realize it? And I think that there should be an answer to these questions. And when one finds those answers, I believe this will be also the key to quantum gravity. So thank you for your time and stay with physics.